Hello. In this video, we're going to be talking about effective nuclear charge. At the end, we should be able to interpret what the effective nuclear charge is. We should be able to calculate it. We should be able to use our periodic table to describe trends within effective nuclear charge. And we should be able to use effective nuclear charge to explain trends that we see in other properties within our atoms and elements within our periodic table. So the effective nuclear charge itself is basically how much nuclear charge an electron feels. Remember that in our nucleus we have protons and neutrons. The protons are going to have a positive charge, and that's what's going to be pulling electrons in. That's that attractive force that we'll feel. So this is an attraction between the positively charged nucleus and the surrounding electrons. The greater that attraction, the greater the nuclear charge, the more electrons are going to be pulled in. Okay? Greater attraction due to greater nuclear charge. More pull on the electron density. Okay. So, like I said, it's going to basically describe our pull of those electrons. And the thing that's going to most greatly affect how effective the nuclear charge is how many protons we have and the distance the electrons are from the nucleus, and then how many electrons are in the way of that nucleus and the electron itself. So 3 factors in effective nuclear charge. We're going to have our number of protons, distance electrons are from the nucleus, and then electrons between the nucleus and the electron in question. When we're talking about effective nuclear charge, we're looking at it as like an electron, a bi-electron basis. So this electron has this effective nuclear charge, this electron has this effective nuclear charge, so on and so forth. So different electrons within our atom will have or will feel different effective nuclear charges. It's not based on the atom itself, it's based on the electron and where it is, what's in the way of it. We can kind of think about our protons. Our nucleus itself is kind of like a light bulb, and then electrons in between the proton and the electron in question are going to be like a little shield kind of dimming that light or that attraction. So electrons between the nucleus and electron in question shield the nuclear charge. Okay, this will lead to a smaller effective nuclear charge. More electrons in the way, the smaller our effective nuclear charge is. We call this screening of the nucleus. Okay, and it's by the electron itself. Usually when we're thinking about the electrons that are screening our nucleus, we're thinking about core electrons, as the valence electrons are much more loosely bound and don't get in the way of other valence electrons. So our core electrons are the ones that do the most screening of the nuclear charge. Okay, valence electrons don't screen as effectively. Okay, and then this idea of the screening of the nuclear charge, the effective nuclear charge, is what most of our periodic trends are going to be related to. So most periodic trends are based on effective nuclear charge. Okay, so let's look a little bit more at the electron screening itself. So if we look to this graph on the right, we can see, there we go, zoom in on that. So we can see our radial electron density versus distance from the nucleus in angstroms. And we see that our 1s electrons are going to be very, very close to the nucleus. And then our 2s electrons also have a significant amount of electron density that is going to be close to the nucleus right here. And then our 2p electrons are a little bit further. So those electrons generally that are going to be closer to the nucleus are going to shield the nucleus more than those further away, right? They're better, they're more effective at shielding or screening our nuclear charge. So electrons closer to the nucleus are more effective at screening nuclear charge because they spend more time near the nucleus. So our s electrons are usually better at screening our nuclear charge than p electrons. Okay. And then our valence electrons, those are very, very far away from our nucleus, so they're going to shield the least. Or screen the least. Now, lots of calculations can be done to do this. Very much more advanced calculations can be done to this, but we're going to use a simple means of calculating our effective nuclear charge, or determining our screening constant. So our simple means of determining effective nuclear charge is through the use of the equation Z effective is equal to Z minus S. This is our effective nuclear charge. This is our atomic number. And then this is our screening constant. Okay, and by a simple calculation, we can figure this out, and it is in pretty good agreement with what they find experimentally. So let's look at how we determine our screening constant so we can know exactly how to do that. So our screening constant itself It's more than just a simple value. It's based on where the electrons are. So as I said, electrons that are close to the nucleus are going to screen more. And even though a more effective calculation can be done if we take into account our different types of electrons, we're going to still go with a fairly simple means of calculating this without thinking about our types of electrons as in S, P, D, or F, but just thinking about them in terms of what shell they're in. So for Slater's rules, we use the shell the electron is in order to determine screening constant. So to determine the value of S, we use the following steps. 1. Electrons with the same N value as the electron in question will have a screening constant of 0.35. So S is equal to 0.35. So each one. You do not take into account the electron that you're looking at, right? So you don't include that in the calculation. Don't include the electron in question. And then next, N minus 1 electrons, S is equal to 0.85, and then all other core electrons, S is equal to 1.00. So when we think about how good of a calculation this is, we can compare our Z effective using a couple different ways. So our black line is our charge of our nucleus, and our different methods of calculating our effective nuclear charge is shown in different colors. So if we are talking about our Slater's rules, that's going to be in yellow. So we see in yellow, it's actually in very good agreement with this blue line. Okay, the blue line is using advanced methods to determine the Z effective. And then this green line right here is using the a simple equation to determine it, where you just take S equal to the number of core electrons. But we don't use that method because it's not a very good method. So Slater's rules, pretty good agreement with our advanced methods for determining effective nuclear charge. And then we can also use advanced methods right here in red to determine our core electrons' effective nuclear charge, but we're not going to look at those. We're going to stick with our Slater's rules, and we can see there's this funky dip between 10 and 11. All right, so right here, this is number 11, our element number 11, and this is when we go from neon to sodium. So what happens when we go from neon to sodium? Well, going from neon to sodium, we have a significant decrease in our effective nuclear charge because now we've gotten to another shell. Okay, so in general, if we're thinking about our trend for our effective nuclear charge as we go across the periodic table, it's going to increase as we go across the periodic table. So trend the effective nuclear charge increases going across the periodic table. And then looking here to here, there is not a significant difference. So there's not that much of a difference going down. It's a little bit, but not much. However, if we were going to say that there's a trend, because there is a slight trend, as we go up the periodic table, we increase in our effective nuclear charge. But it's very slight. Okay. So the way that you think about this, why we have this big jump here, is when you're going across your periodic table, you're increasing your number of valence electrons, but you are not increasing your number of core electrons. So if we were to compare, for instance, let's take lithium versus neon. Lithium is 1s2, 2s1. Neon is 1s2, 2s2, 2p6. So we're solving for our effective nuclear charge here. Our number of protons in lithium is 3. And then our shielding constant, this one electron right here, does not get included because it's the one we are observing. So we're only going to count these 2 electrons here. So it's going to be 2 times by 0.85, as our greatest n value is 2. This is n minus 1. And what we get is a value 1.3. And then for neon, our atomic number for neon is 10 minus our constant. So we have 5 electrons here, 2 electrons here, so a total of 7 electrons, and our greatest n value, which has a shielding constant of 0.35. And then we have 2 electrons in the 0.85 and minus 1, which gives us a Z effective of 5.85. So a significantly larger Z effective for neon versus lithium, because in both cases we have the same number of core electrons, but we're increasing our number of valence electrons in neon, which doesn't have a very significant shielding constant, but we're still increasing our number of protons, which has a full positive 1. Okay, that's everything for effective nuclear charge. Hopefully you guys understand a little bit better, and I will talk to you guys later.